When you want to go beyond the basic bolt-ons, you'll find that tuning with the mass airflow sensor is quite problematic. The mass airflow sensor requires a specific size and shape of intake around the mass airflow sensor so the computer can correctly determine the number of grams per second of air going into the engine. This is a problem because this housing actually becomes quite restrictive, particularly in the case of forced induction. And in some supercharger setups, we've seen the stock plastic intake piping collapse from the vacuum draw from the restriction that this has caused. So Honda have created a great new method of tuning your car, and instead of using the mass airflow sensor as the primary sensor for fueling, we have switched it to the MAP sensor for the primary tuning of fuel. This means that you can design the size and shape of your intake for any application that suits you. The mass airflow sensor still needs to be in the airflow because it contains the air intake temperature sensor, but you're not restricted at all as to the size and shape. Hondata's race calibration is great for boosted vehicles, like the supercharged Civic Si. Let's put it on the dyno and find out why. The supercharged Civic comes standard with a returnless fuel system and is tuned to run with large injectors. It also makes around 300 horsepower, which is about 50% over stock. Let's do the dyno run again and take a close look at what happens to the fuel pressure. In a naturally aspirated car, your fuel pressure will stay at 54 psi the entire time. But as you can see from this dyno run, the fuel pressure starts at 54 psi and drops to 44 psi because the fuel system is not capable of delivering the amount of fuel you need. In addition to that, you have 10 psi inside the intake manifold. So whereas with a naturally aspirated car you had 54 psi differential from the top to the bottom of your injector, you now have, at the top of your average range with the forced inducted vehicle, 44 psi at the top of the injector and 10 psi at the bottom, meaning the effective pressure of an injector has dropped from 54 psi down to 34 psi. So the flow capacity of your injector has changed tremendously. This is really hard to tune, if not near impossible to tune, with a mass airflow calibration. The race calibration that Honda provides with the Flash Pro is very easy to tune for this. From the new calibration button, choose Civic Si Race. Here are the fuel maps. This is the low cam fuel for the low speed, low lift, low duration camshaft. There are 5 different fuel maps for when the cam is positioned at 0, 15, 30, 40 or 50. In general, the maps for emissions, or good emissions, are 0 and 15 all the way up to 30. The maps in which we generate maximum power are typically 30, 40 and 50 degrees. The area we tune, naturally aspirated, is this section here, columns 10 down to columns 1, which is 11 kilopascals all the way to 102 kilopascals. The area we tune for boost is this area here, 184 kilopascals down to just above boost, just above naturally aspirated, 102 kilopascals, which is around 10 pounds of boost. Let's have a look at the tuning process. From the calibration window, choose VTEC and set the VTEC point high. Go to the low cam map and set, under your load conditions, a cam angle that's fixed. In this case, Control J for adjust, and we're going to set the cam angle to 30 degrees. Now we go back to the low cam fuel map, we go to the 30 degree fuel table, and we're now ready to tune all the fuel for the 30 degree cam angle. If you're tuning for boost, as I said before, you'll tune this area here. But let's go back to the example where we were losing fuel pressure. How do we compensate for that? Well, as we go up the rev range, we're going to need to add more fuel. The numbers that you see in these tables here relate to the amount of fuel delivered. You double the number, you double the amount of fuel. Same way, if you add 10% worth of fuel, you'll change the air-fuel ratio by 10%. So how do we compensate for dropping fuel pressure? This is how we do it. Let's select this area from 5,000 RPM to 8,500 RPM. By pressing Control I, we can add, let's say, 6% fuel. 1, 2, 3, 4, 5, 6. And then we can add some more fuel from 5,500 RPM up. 1, 2, 3, 4, 5. And then just keep on adding more fuel as we go up the rev range. And as you can see, we end up, Control I here, ending up with some very small fuel maps, very smooth fuel maps. So we can edit by clicking on the RPM and down these columns here, or if we want to add more fuel specifically under boost, we can edit in these areas here and hit Control I for increase or Control D for decrease. You might find in the lower part of the rev range, let's say between 2 and 3,000 RPM, you need to reduce the fuel, so Control D for decrease. Now I've developed a fuel map for my 30-degree cam angle, which gives me great power for 30 degrees. At this point, I hit Control A, copy everything, go to the 40-degree map, and paste in my tuned maps. I then go to the cam angle for 40 degrees, and just so we can see, I'm going to change all my loaded area to 40 degrees. Control J, Tab, Tab, 40. I then go back to the fuel map for 40 degrees, redo my dyno runs, and make all the changes I need to fuel and also ignition to give me the maximum power. In the end, I'm going to have 5 dyno runs, each for 0, 15, 30, 40, and 50-degree cam angle maps. Now we have to combine all of those dyno runs and find out where we make the most power. So let's enter the cam angle at which RPM we make the most power. So our dyno tells us from 5,500 RPM we make the most power at 10 degrees cam angle timing. From 5,000 RPM to 3,500 RPM we make the most power at 15-degree cam angle. From 3,000 through to 2,500 RPM we make the most power at 30 degrees. 2,000 to 2,500 RPM we make the most power at 40. Under that we make the most power at 20 degrees. If you have a look at the cam angle map in 2D here, you'll see that it looks quite jagged. Cams don't move in a stop-start fashion like this. The cam angle needs to be swept or moved smoothly. So we now change this and we smooth out the cam angle. Let's take this point here for example. This point we're going to decrease, and I'm going to do this by eye, just by pressing the Control D key to decrease and increase to smooth things out. This point here is a little high. We need to bring this one down a fair bit, and we need to bring this one up a fair bit as well. This point here we need to add a little bit more cam timing. This point here, a little more. I think you get the idea. We are smoothing out the operation of the cam, so the cam now sweeps smoothly from this point here through to this point here. We might find this actually doesn't need to be 40. We might find it needs to be a couple of degrees less. Smooth out a little bit. So once we build ourselves up a composite cam angle map like this, we'll dyno it with all these cam angles. Then we'll do a second run in which we'll select all the cam angles and we'll bracket it. Anyone familiar with photography will understand the word bracket, in which we will add 5 degrees to the cam angle maps, dyno it again, we'll subtract 10 degrees from all the cam angle maps, and we'll then see if there's any parts of the curve where we've made any mistakes and can do some corrections. Now we have the best overall power for the low cam, we need to dyno the high cam. So from the calibration menu, under VTEC, we set the VTEC point low. In this case, we'll set the VTEC point to 3,000 RPM. Okay. And we now go and dyno the high cam, setting all the fuel maps to respectively 0 through 50 degrees on the high cam to build up a composite map for the high cam.